Yeah, so hello everyone. So in this demonstration, we are going to study about uh, we are going to work on a transonic flow over a NACA 0012 airfoil in ANSYS. So let's start. We have all the things. Maybe I'll just download them. And I'm so sorry for the background noise. I'm living in a common shared apartment. Uh, so now let's Uh, let me give you some workshop description. The purpose of this workshop is to simulate transonic flow over a two-dimensional NACA 0012 airfoil and compare the result with experimental data. This workshop solving a compressible flow because obviously it is more than Mach 0.3, 0.4, after which the airflow becomes compressible. Monitoring lift and drag, again comparison with experimental data. To understand how to solve, learning objectives would be to understand how to solve compressible flow and how to compute lift and drag in external aerodynamics applications. Problem description: the case considered here is flow around a NACA 0012 airfoil at a 1.55 degree angle of attack and free stream Mach number of 0.7. The airfoil drag and lift coefficient are the primary quantity. Drag and lift coefficient. Okay. The pressure coefficient over the airfoil surface will be compared with experimental measurements. Okay, so computational domain, if we see uh, airfoil geometry, NACA 0012 is around 1 meter in chord length, 1 meter. Computational domain, okay, so it's 20 meters ahead of the airfoil, 24 meters behind, and 30 meters above and 30 meters below. Mach 0.7, angle of attack is 1.55. For use in fluent meshing, the geometry is extruded in the z direction at a distance of 1 by 10th of the chord length, and symmetry conditions are applied to the side boundaries. We will apply far field boundaries at the outer boundary of the domain shown in the previous slide. Is something that I see. The simulation result will be compared with test data from a wind tunnel. In the test, the total pressure was reported to be 100 and uh, it's around 100,000 pascals. The total temperature at 311 Kelvin. How much is that in Celsius? It is around 40 degrees Celsius. Uh, yeah, around 40. And the Mach number was 0.7. 273, 25, 35, yeah, around 40. Based on these values, the static temperature and static pressure can be computed using relation to the right. Okay, we have got some equations. Maybe I'll put them in thumbnail. The speed of sound in air is at 283 Kelvin, which I'm sure it's 10 degrees Celsius. 330 is approximately equal to 338 meter per second. For an airfoil chord length of 1 meter and Mach 0.7, the Reynolds number is around 12 to 10 raised to the power 6, so the flow is turbulent. Okay, Reynolds number is something that helps us define if the flow we are dealing with is laminar or turbulent. So we will first start our fluent launcher window, and we need to start it like directly as was informed to me by my senior. Fluent. Okay, let it start. Okay, I would really like to change my working directory over here. Let's see, where is my tutorial, and how should we transonic flow NACA 0012. Just simply name it NACA 0012. and we select folder, and we go inside, select folder, fluent root path. I'm really not sure how this thing works. So parallel settings, remote, scholar. Let's see what our instruction file tells us. Just select meshing mode, double precision, solver. Just select 3D options, double precision and meshing mode. Display mesh after reading. Okay. Use job scheduler and start server. That's different. Okay, parallel processing. It's 1 and 4. Are they asking for GPUs? Processes is 4. Okay, GPUs per machine. I'm not sure. Okay, we can click start. It's enough. One tip of advice is anytime when you're dealing with CFD, CFE, always keep your system plugged in. Okay. Oh, it's still not opened. Here we have to select units as meter for some reason, and select units to meter. Okay, we'll see that. And well, remove this. And okay, units. Let's go. Task page. Now select the watertight geometry workflow and select to M and import. I had to select geometry from somewhere. From where can I select geometry? Nothing is enabled and I'm seeing a very weird page. Let's quit it from here and start it from workbench. I don't know why this my scroll does not work over here. So fluent with fluent meshing, put it over here. If I double click over here, oops, mesh. Mm-hmm. Double precision. Solver processes 4. Meshing processes 1. And display mesh after reading, yes, and meshing mode. I think so this is meshing mode. Let's see. So from here, select watertight geometry, click import geometry, and first of all, our screen is a bit small. Okay, units set to meter and import file. Uh, do we have all the files? No. So one second, let me download the files. 1, 2, and 3. Airfoil. So now I have the files, and let's go to program files, and do we need to go to downloads. Nope. Yep, I have downloads over here, and airfoil, and click OK. I'm anticipating it might give me an error, fail to import geometry. In that case, you will need to import it again. I mean, that's how these systems work. Yeah, just wait for it. Maybe skip the video if you want. Yep, finally imported. I'm already afraid. Okay, let me close some unwanted things. Maybe they are sucking up my bandwidth over here. Just yep. Sorry for that. I think so. Yeah. Another thing I have open is Solid Edge, which is very heavy. Okay. So in this file, you will need to add local sizing. Hmm. Import add local sizing. A local face size will also be applied to the airfoil surface to prevent the mesh from becoming too coarse near the airfoil surface. Would you like to add local sizing? Obviously, yes. Now, enter the following. It's airfoil max face size. Airfoil max type is face size. Do I have it over here? Okay. Size control type. Yep, face size. Airfoil max, and what do I need to airfoil for airfoil lower and upper? You don't need to select control for selecting all of these things. Okay, growth rate is 1.2 and target mesh size is 0.015. We have already set the 0.015. Okay, and I'm a bit worried that yeah, this is what happens when you have multiple monitors. Add local sizing. So now you can see that the airfoil has been modeled with a, we have a trailing edge that is flat. It's not meeting at 2 points. Okay, the airfoil has been modeled with a thin 0.7 mm trailing edge, and the local face sizing will be applied to produce fine meshing solution in the important trailing edge region. Okay, now we need to create uh, another local sizing, that is for TE approximation. TE prox, and that would be size control type would be proximity. So we are adding some things in the proximity. Local min size is 0.0005, 0.0005, and max size is 0, and maximum size is 0.5. Cells per gap is 2. Cells per gap is 2. Scope to edges and face on airfoil TE, and then add local sizing. Now this is hectic really. Oh, it's done now. Set minimum maximum size to, and now let's generate the surface mesh. Minimum size to 0.0000. No, it's 3 times 0, right? Yeah. 5 mm maximum size is 0.5, and curvature normal angle, we need to make it to curvature, and curvature normal angle would be 12. Draw and generate surface mesh. Now this is heavy. So yeah, this thing takes time. Yep, done. I think so. Remeshing, doing its things. Should I really do it? Yeah. Yes. So you see, we have meshed it with finite meshing in the area surrounding the airfoil. You see that here the mesh is much more finer. Okay, now we can describe geometry. The geometry consists of only fluid region, and in the next step we will assign boundary names and types to various zones. The geometry consists of only fluid regions with no voids, and change all fluid boundaries. Type from wall to internal. No. Do you want to apply shared topology? No. Just create describe geometry. Update boundaries. Boundaries were assigned name selections in the CAD file. So the correct names and types were preserved during the import geometry task. Update boundaries. Yeah, I have something like this. Remember that hovering the mouse button over the boundary name list in the input panel will highlight individual zones in the graphic windows for easy visual identification. So it is saying something like this. Let me zoom over here, and to show you what I actually mean is this. See, I move. But I'm still not able to understand how does my airfoil. Oh, okay. My airfoil is something like this. Now regions. In update, regions change the name of the fluid region to fluid. Click on update boundaries and region name to fluid. Update regions. Now add boundary layers. Right click on update region and add an add boundary type task. Insert task names. Add boundary type. Okay. Add boundary type. So we will add pressure far field here and we will change the name to. Didn't I add boundary layers? I did not add boundary layers. Okay, just first change far field. Zones far field and far field 47. A pressure field. So yeah, I have far field over here. I do not have far field 47, but I am pretty sure that this is the far field they're talking about. Oh no. Okay, just select it once more. Far field. And this is pressure far field. There is already another task name far field. From where can I just delete it? Oh, revert and edit. My laptop is really dying by what I'm doing on it. Update. Okay. Now generate volume mesh. There must be some warning message which could be softly ignored. Warning. The provided level name already exists. The name was changed to far field 1. Okay. The far field zone was separated during the region creation based on the angle between the faces. It was easier in solution mode just to have one far field boundary. Now create volume mesh. Offset method. Now select uniform offset method type. Select uniform offset method type. Enter 20 for number of layers. Where the hell is that? Boundary layer setting trials and generate the volume mesh. Create. I remember in my last. Just do it like this. Its volume setting and boundary layer setting were on fluid walls. I'm not getting anything like that. Hmm. Okay, let's see. I have something. Now, write mesh and switch to solution mode. And I'm pretty sure here I will not be having the things that I need. Click on switch to solution. Yeah, I've done it. So just click to solution. Okay, it will automatically write it over there. Meshing information is transferred to the solver. The GUI changes from the meshing mode to solution mode. Console warning. Ideal gas law will be enabled in a later step, so this warning can be ignored. Alright. Console warning during switch. You know, read, write, autosave, import, and export. And so here we will be going in disorder domain physics solution result. Okay. So in domain, our first step is always perform a mesh check. Done. Perform a quality check. And the mesh check returns no error. Quality was already verified in meshing, so there is no need to repeat here. If a mesh file is read that was created by another software, a quality check can be performed, as demonstrated in uh, somewhere. Now, operating conditions. In the physics tab, activate energy. Energy. Set the operating pressure to 0. Now, operating conditions. Where is operating? Yeah. Operating pressure to 0. Okay. So in fluent, the absolute pressure is equal to operating pressure plus gauge pressure. Operating pressure is set here and gauge pressure is what the solver calculates. For incompressible flows, the operating pressure is typically set to atmospheric pressure. This allows the solver to compute only the smaller gauge pressures, which helps to prevent round-off errors. For compressible flows, the solver needs to use the absolute values in the calculation. Therefore, it is sometimes convenient to set the operating pressure equal to 0 so that the absolute pressure can be used as boundary conditions. Okay, let me read it again and myself understand what it is trying to say. For compressible flows, the solver needs to use the absolute values in the calculation. Therefore, it is sometimes convenient to set the operating pressure equal to 0. So that, okay, for incompressible flows, for incompressible flows, the operating pressure is typically set to atmospheric pressure. This allows the solver to compute only small gauge pressures, which helps to prevent round of errors. Okay, we are not taking into account gravity over here, and we click on okay. Was that into pascals? Yeah, yeah, yeah. That was in pascals. Now, in the physics tab, click viscous. Where is viscous? Hmm. Viscous. K omega. The Reynolds number is 12 into 10 raised to the power 6. Now, where is the Reynolds number over here? So, turbulence model is required. Enable ST omega model SSTK omega, SSTK omega, set production limiter, and yeah, nothing else. SST omega model is preferred always for aerodynamic flows. Then create edit. Opening mesh panel. Click materials and select ideal gas for density. Click what? Click materials. Ah, ideal gas. And viscosity is Sutherland. Sutherland. Okay, I never knew. The Sutherland model of viscosity is well suited for high-speed compressible flows. For simplicity, Cp and thermal conductivity will use constant values, but ideally in high-speed compressible flow modeling, these should be identified as temperature dependent. Three coefficient method. Okay, and do not disturb it, just click OK. I would rather click here, change, create, and once it has returned to its previous state, I would simply click close. Only 14 more pages left, guys. Please bear with me. I think I'll wrap it up in 45 minutes. Physics, cell zones, and boundary conditions. Materials defined are complete, so proceed to zones. The default material of air will be used, so no need to set any cell zone conditions. Click boundaries and open the boundary conditions panel for far field boundary. At pressure far field boundaries, required input are the Mach number, static pressure, flow direction, turbulence BCs, and static temperature. So in zones, click boundaries, and I must have some path. Try to open it. Yep, I open it. Far field. Was any name changed? No. So gauge pressure in Pascal is 73048 momentum. 73048. Mach is 0.7. We have already said this is the system is XYZ component X component of flow direction. Whoa, it's a very specific value. 0.12378. Y component 0.02079. Z is 0. Here we have 1. Here we again have 1, and here we intensity and viscosity ratio, and we click apply, and then that's done. Click boundaries. At pressure field boundaries required, because the angle of attack is the flow direction is okay, so we are changing this because of an angle of attack. So maybe you might need to calculate your x and y coordinates based on the angle of attack you have. Here it is 1.55 degrees. Okay, in thermal also we need to make some changes, and 283.24. It's 283.24 Kelvin. Apply and close. Okay, now go to solutions. Okay, so click methods in the ribbon to open the solution method. Scheme is coupled, and just verify. least square based cells, second order density, pressure, second order gradient is second order upwind, second order upwind, first order upwind, and high order term relaxation also we need to select here. Leave the pressure velocity coupling, activate high order term relaxation, wrap phase gradient correction was already activated by default because of the mesh has polyhedral cells. Use of coupled for pressure velocity coupling is recommended for compressible flows. The pseudo transient and high order term relaxation option often help to stabilize the convergence behavior. Solution. Now we go into definitions and add force report, drag. Okay, the drag coefficient. Yep, coefficient of lift half rho v square a of drag. The drag coefficient normalized force on selected surface area. So the drag coefficient is the normalized force on the selected surfaces in the direction of the flow. So coefficient of drag is equal to force of drag divided by half rho v square upon a. Rho is the density of the air, velocity is the velocity of the air flowing over the wing, airfoil here we should say, and area is the air. A is the area of the airfoil. Now please name it CD report because it's coefficient of drag. CD report, not report. Neither we are Russian nor we are Spanish. Drag coefficient. Okay, so I can find drag force or drag coefficient, whatever I want. Force vector, and yep, again those critical values 0 0.99978. Y would be 0 0.020, 0 0.02079, and we select upper and lower airfoil. For that no need to press control as I did by mistake. Report plot, and yeah, just 079, just click OK. Yeah, it's simple as it is. Okay, report defining for lift coefficient. So first we have drag coefficient, now lift coefficient again. So I need to find, we go into, no, sorry, not here, new force report and lift. Here we again change the name, CL report, and X is minus 0.02079, 0.02079, and Y is 0.99978. CL lift coefficient and both airfoils we have to select again. Please don't, no need to press control, report plot, and okay. Reference values for drag and lift coefficient. Double click reference values in the tree to open the reference values. Where is reference values? Okay, here we have reference values. Select far field under compute. Under compute, where? I open something area. Nope, it is. Oh, sorry. You have to select reference values, not reference frames. Compute from far field. Now area is 0. Density, length Here my area is 0.1. Ratio of specific heats, reference zone. Okay, the density, velocity, and area values used by Fluent to compute drag and lift coefficient are based on the entities in reference values. We want to use free stream values of density and velocity, so it is convenient to automatically fill the panel based on the far field boundary. In other cases, one or more values can be manually edited in at any time should boundaries values be unsuitable. Okay, the area is based on the chord length, which here is 1 meter, and the depth of z directions is therefore enter the value of 0.01. Okay, I already did that. Solution, initialize and calculate. Click on solution, initialize at time t equal to 0. Warning, convergence tolerance of 0 not reached. Okay, remember the message about the hybrid initialization is just a warning, not an error. It is okay to proceed. Enter 50 iterations and yep. Now here, please keep no time scale factor is what was this time scale factor? Okay, 50. Here, please keep your machine plugged in. It's going to consume so much energy. It's gonna blow off. Check case and click when iteration is complete. Files, write data, case in data. Calculate. Guys, this is going to take time, and let me put myself over here so that we can see some things. Yeah, so this is what CL. Coefficient of lift. This is coefficient of drag. I'm taking a nap until this is done. Yeah, so we see that the value is somewhat reaching to a steady value. Yes, calculation complete, and let's see. Yep, I'm getting coefficient of drift, no sorry, drag something around 0.01, and coefficient of lift is, wow, it's a very poor coefficient. The residues are decreasing, but maybe slower than you would like, and the drag and lift meters are still changing. Use more aggressive settings. Increase the time scale factor to 10 and run the calculation. And do 100. Okay, increase and click calculate. Yep. Warnings. The settings have changed in Fluent. How would you like to proceed? Use settings changes for current calculation only. Use settings changes for current and future calculation. For current calculation only. Now again. let's see. I think this is going to fall again. Yeah. See, we are getting a better depth. The sensor is convergence criteria, but the drag and lift monitors are still changing. Solutions, residuals. You know, I can show you one thing. You guys have been following the speed of this progress bar while my system is plugged in. I'm just gonna momentarily plug out my system and then let's see what happens. See, it's stuck at 51. Ah, even it's not stuck. Yeah, it has literally stuck on 51. Oh no, and it died at 51. Plug it back again, bro. Plug it back again. It said calculation complete. Give me power or shut the hell up. Now let's see residuals. To perform more iterations, open the residual panel and reduce the criteria for equation with the highest value. More iterations, open the residual panel and reduce the criteria for the equation with the highest value. So it is having something like energy and what what do they want me to do? A number of iterations to store window. Yeah, I mean I'm getting something like this only. The energy residual reaches the new convergence criteria and the drag and the lift report plots are steady. Leave it mass balance. Okay, just leave it. The solution is converged, so move from the solution tab to the results tab and click fluxes to compute the mass flow rate. To the results tab and click fluxes. Fluxes was somewhere over here. Yep. Mass flow rate. Net results. What? There are no distinct inlets and outlets in this problem. Just the far field boundary. It would be negligent to simply decide that 0.002 kg per second must be okay because it looks like a small number. The extent of the computation domain in the y direction is 60 meter as seen to the left. A better way to evaluate the imbalance is to use the boundary values for density is equal to 0.9 kg per meter cube and velocity equal to 240 meter per second. The origin of these values is shown in slide 25 and okay, or it would also be possible to compute average values in surface integrals such that the mass flow rate through a 60 meter cross section is 60 meter cross 1 meter direction into 240 meter per second into 0.9 kg per meter cube, which is around 13,000 kilogram per second. Here the imbalance is several orders the magnitude lower, so the solution has achieved a good mass scale. Okay, far field, and if I click compute, mine is negative. It's something else. There might be some issues, but now you get an idea how to like do certain things that you might want to do. Expand report definitions and in the solution branch of the outline view and double click on CD report. Just click on close. Reports, report definition. Double click on CD report. In the CD report panel, click compute. The drag coefficient value is displayed in the console. Repeat for CICL report not shown as. Just click on compute once and let's see the certain things. So what is the CD I'm getting? Click on compute and nothing happens. So click on OK. Okay, we can see contours now as well. Display contours of pressure on symmetry. Note the high static pressure at the nose and the low pressure at the upper suction surface, which is expected as the airfoil is generating lift. Display contours of Mach number. Note that the flow is locally supersonic. Mach number greater than 1.0 as the flow accelerates over the upper surface of the airfoil. Okay, so I will go on contours, new, new, pressure and static pressure. There is no contour of Mach numbers. Smooth, banded, no. Save display. Contour object is not valid. Oh, okay. I think so. I need to select just everything. Now save display. Hmm. Do anywhere we see contours of velocity? Contours of velocity. Where is velocity? Velocity, magnitude, far field. Save and display. But it is somewhat not displaying. Okay. Here must be some reports, maybe animation. There is no contour report plots. Huh, I see a contour over here. Why can't I simply see the contour? Ah, I was seeing. Okay, contour of static pressure. See, and it is absolutely. And why do we only have velocity magnitude? Okay. It can only display one contour at a time. And it is display. contour 2. I can name it. I think so. I need to again select everything, then save and display. Yep, clouds, and see, we can see over here we are having a much higher speed than on the lower edge, because on the upper edge of the airflow is accelerating. That's what creates the low pressure according to Bernoulli's theorem. ISO surface. So we see some contours over here. Now surface. In the result step under surface, go to create ISO surface. In the result step under surface, create ISO surface. In the ISO surface panel, under from surface, select all the airfoil surfaces. In the ISO surface panel, under from surface, new surface name, from surface. Oh, select all the airfoil surfaces, upper, lower, T, upper, lower, and T. New surface name is Z equal to 0. Airfoil. Surface of constant is mesh, and x coordinate. No, we need to see the z coordinate, and ISO value is 0. Keep it 0. Max min thing is doesn't matter, and create. This creates the intersection of z equal to 0 and the airfoil surfaces, which is a curve that can be used for xy plots. Result xy plot. So did we get anything in the results? Plots. So yep, we are getting xy plot, and again we need to create a new xy plot. Node values, there's nothing to be changed. It is important to resolve the viscous sublayer of this application, so y plus is equal to 1 is desired. Where values seen here in the range of 3 to 6 might be a bit high, and for a real problem instead of a workshop exercise, it would probably be advisable to create a new mesh with a smaller first layer height. Make an xy plot of pressure coefficient. Click on curves to change the plot to a solid line. Now where is curves? Uh-uh. I promised 45 minutes. Sorry for running over 15 minutes. Maybe it is going to go spill over more 10 minutes. Make an XY plot. Click on curves. Something has been. Okay. No, XY plot. New. Where to click on curves? Okay. Click curves and change the plot to a solid line. Okay, so we are just not able to plot the XY. I would really leave it here because I think so it will be consuming a lot of useless time. So maybe if someone knows how to deal with this XY plot, so maybe I'll just give you an idea. Copy the files test data.xy to test data bottom. Oh, it's just for testing with your input case. Click load file, navigate to the XY file, and add them to the plot. Blah 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 blah. So yeah, so that was all about this tutorial, and please make some comments down the line. Not say really like, but yeah, anything you do, it's just a click for your end, but it could make a much difference, um, a lot of difference at my end. Okay.